Log on, tune in, find out. Another good idea from Cambridge.
So I'm very happy to announce as the first speaker of the morning Jérôme Le Rousseau from Orléans, and he will talk about the Carleman estimate for stratified media, the case of a diffusive interface. Please.
Thank you, Mikko. Well, good morning, everybody. Well, last night we had a very nice time in a wonderful place, and thanks to Lassie's speech, we had the opportunity to thank the organizers, but I wish to do it again today, and because I feel very honored to be here for this workshop and to speak in front of this audience. So I wish to thank the organizers of the whole semester and of course of this workshop. What I want to talk about today is Carleman estimates. One of the reasons is that we've heard quite a bit about them in the past 2 weeks. I mean, for the people who were here for the first week, there's been some lectures in which they appeared, and I want to talk about cases when coefficients are non-smooth, in the sense that they have jump discontinuities. And here there'll be a little twist, is that on the interface where the discontinuity occurs, there'll be additional phenomena. This is joint work with Mathieu Leoto, who just finished his PhD in Paris, and Luc Robiano, who's here, and will also give a related talk tomorrow. Okay. So first of all, even though we've seen those before, let me remind exactly what Carleman estimates are, because they are actually in their form not difficult to understand. They are energy-weighted estimates, in the sense that here's my operator. Let's take it of order m, so it's a differential operator of order m. And I have this exponential weight here. This is what is found usually. And tau is a parameter meant to be large. Phi is has some suitable properties, and we'll see that in a bit. And of course related to the operator p. And what do we see here is that the L2 norm of this weighted operator dominates several things. When you take beta equals 0 here, there will be the weighted L2 norm, and then you will have a weighted H1 norm until you reach m minus 1. When it's an elliptic operator, you have a chance. You should be able to get equality with m. Okay, and as I said, there are necessary conditions and there are sufficient conditions. And this goes back, of course, to the work of Thorsten Carleman himself, and it also owes a lot to the work of Lars Herdemander, especially for those necessary and sufficient conditions. Let's be simple. Let's look at a second order elliptic operator, namely the Laplace operator. And this is what you would find usually. So we've seen other types of estimates here where those powers here were weaker. I mean, in the sense that instead of having tau 3, you could have tau square, or sometimes even tau. I think, for instance, of the talk of Colin Guillermo. And also when there are so-called limiting Carleman weights, the conditions you put on phi can be much weaker, and you won't recover those high powers. Here I'm going to consider those type of estimates with those type of powers, which means that in some sense you lose half a derivative. I'll show that it's related to subellipticity a bit later. Okay, so once again, the weighted L2 norm of the PU dominates the L2, the weighted L2 norm of U and the weighted H1 norm. Okay. For convenience for the analysis, but one doesn't have to do that, but I will do it here. I'll change my large parameter into a small parameter, introducing its inverse, H, and then the estimates will look like this. So I multiply, in fact, my second order operator by H2, So here, that's why I have H4, and that means I'm going to consider the semi-classical Laplace operator, and then those are the powers that I will obtain. Okay, now let me talk about the setting of this talk. What we want to consider is a medium. It could be on a manifold, but here for simplicity, let's look at an open set of Rn with boundary. In this case, I mean, on a manifold, we could also consider things without boundary. We have an interface, smooth, that separates the medium into two parts. We can also consider several interfaces, but they should not cross. And in each part of the medium, we have a smooth elliptic operator, and we also have something going on at the interface. Namely, what we consider is on each side of the interface, we have those things. So C, so what is C here? Basically, it's the, well, in Rn, it would be divergence C grad, but on a Riemannian manifold, it would be the Laplace-Beltrami operator with some metric, and then you have this conformal factor C that would depend on X, and that would have a jump across the interface S. And on the interface, this is what we have. We have another elliptic operator, and this time the interface is a submanifold. Therefore, this is a Laplace-Beltrami operator for this conformal factor. And there's, of course, a source term. And there's also this additional source term that comes from what goes on one side and then the other. And then there's a small parameter delta. And also what we assume, so this is a transmission problem, you know. And we assume the continuity of the trace. That means all the values are the same on each side, I mean, at the interface. And if you send delta to 0, what happens is that this would turn out to be 0, and this would be the traditional transmission conditions that you would have if you consider an elliptic problem with non-smooth coefficients. But here, what happens is that this acts as a source for a diffusion process along the interface. Why do we consider that? Well, first of all, because it's more general than what we did before, but that's not the only reason. The reason is that there's been some different papers by Zouazouas and co-authors where they consider such problem for waves, and they had those type of operators. And the way you can understand this type of model is that you would have three media, and you shrink the middle one to 0, and you have you call the thickness, you call it delta, and you let delta go to 0. I mean, this is just heuristic, but this will explain the model. So what you have, if you have this elliptic equation in every region, in the three regions, and the natural transmission conditions will occur at the two interfaces. We have two interfaces at first. We would have the continuity of the solution and the continuity of the flux. And then formally, and I insist on the formally, we're going to let delta go to 0. So since delta is going to be thin, we can assume that what the diffusion coefficients in the middle layer is independent of delta of the transverse direction, which I call xn here. And then we take mean values for both the solution and the source term, and we end up, so we integrate the equation with respect to the transverse direction, and we end up finding this equation, which is what we had at first. And you see that there's this, we keep this small parameter here. And the question becomes, the first model, we know there's unique continuity, we know there is unique continuation, we know that we can derive Carleman estimates and then apply it to different subjects. The main motivation here is actually control theory, but We've seen that, and they are important for inverse problems. So one of the questions we may ask is, can we obtain for this limiting model estimates, and can we have uniformity with respect to this parameter? Okay, so this is our model. And of course, as I said, formally, if you let delta go to 0, we go back to the actual classical transmission problem. But this is not just formal this time. Indeed, if you look at this problem and you let delta go to 0, you will find exactly the solution of this transmission problem. So, and both problems are well posed. We can also consider the associated parabolic equations. And this is for those type of problems that we also want to prove controllability results. I'll explain that in a moment, but I won't insist on those results. I'm really going to insist on the Carleman estimates. So, so we have this interface S, and because of the form of the estimates we're going to show, we're going to have to work globally in a neighborhood of this interface. And so we call M a small neighborhood of this interface. So this will be a manifold with boundaries. And so we're going to consider this problem. And this is the result we're going to prove. Okay. So as I said before, so we're going to show that we can indeed find a well-chosen function, then we'll find a constant, and it will be, the result will be uniform with respect to that thickness parameter delta. So what do we have here? Well, we have our usual terms in the sense that we have the, so this is the solution on both sides of the interface. We have the weighted L2 norm, weighted H1 norm. We also have trace terms. So what goes on at the interface, we have the L2 norm of the trace, we have the H1 norm of the trace, which includes the normal derivative. And then we have on the right-hand side the source term away from the interface, the source term at the interface. I recall that there's a source term at the interface and there's diffusion occurring in codimension 1. And then there's this term, which is fairly, as we shall see, awkward. Because I mean, you see the usual term that makes our life easier is this h power 4, and this has been replaced here by h2 delta 2. Of course, delta is meant to be small, but we cannot choose it as small as we want. And this is the reason why we're going to work in a neighborhood of the interface instead of just in the neighborhood of a point of the interface. And then, well, you know, one of the beauty of Carleman estimates, at least those ones when you have those type of powers usually, is that you can work locally and then you can patch those estimates together. And that's the way to work then, because you don't want to bother about what goes on there. You just prove things here and then where your difficulty is, and then you use more classical estimates and then you patch them together. Here, unfortunately, because of this term, how do you do this patching? Well, you localize things, so then there are commutators that give rise to first order and zero order operators, and you need to absorb them in your estimates. Unfortunately, with this type of powers, this won't work. So we have to work globally in the neighborhood of our interface, and also, this is also why we have this function that is called zeta. It localizes near the interface, which means that this will only be close to the interface, and then when you want to patch this estimate now with estimates away from the interface, then you can do it because this term won't interact. So you see what we do. So we have our interface here, and we give an estimate that is valid in the whole neighborhood of that interface. Okay, this is technical details, but this really did not make our life easy when proving it. Okay, so that's pretty much what I just said. And in the limit delta to 0, we recover previous work that we did with Le Rousseau, where we obtained Carleman estimates for transmission, classical transmission problems for second-order elliptic operators. Okay. Okay, we need some conditions on the weight function. And here, what we want to do is that, in some sense, we want to observe on one side, so that would be on this side here. We want to observe the solution there. And so we take a function that is continuous. So xn here equals 0 is my interface. I look here in local coordinates and have all transverse coordinates in this direction. So I take my weight function to be continuous across the interface. Its gradient should not vanish, and it's actually this is necessary. We've seen in Colin Guillermo's talk there was an estimate with a weight function with vanishing gradient, and this is because he was going for a weaker estimate. Actually, you can prove that for those strong estimates, this is a necessary condition. You cannot obtain such. You can focus solutions at the point where the gradient vanishes, and you make your estimate blow up if you don't, if this is not satisfied. And then there will be a condition that I explain in a bit, which is due mainly to Hermander, and which is a sub-ellipticity condition. And the additional condition that is quite important is that we ask for the slope of the weight function across the interface to grow, to jump at the interface and to be positive. I mean, I want to observe things here. That means I want phi to be large here. So I ask for a large increase of the slopes. Here is an example. For instance, you could take some anisotropic distance, and then suddenly the slope changes. Here are level sets of your weight function. Of course, you would not want to compute your Carleman estimates here, because here, as I said, the gradient would vanish. Okay. So here is good morning. Here is a scheme of our motivation. If we now consider the associated parabolic operator, what can be done is that following a method introduced by Gilles Lebeau and Luc Robiano in the 90s, you can prove controllability of the heat equation, of the associated parabolic problem. You see, you prove this type of local Carleman estimates that we showed for this operator. And then you can prove some interpolation inequality, and Luc Robiano will show those tomorrow. Then this leads to an interesting spectral inequality for sum of eigenfunction of this operator. I'm actually going to write this spectral inequality because I think it's very interesting in itself. So I have this operator, and it has some eigenvalues and eigenvalues and eigenfunctions, J in N. And what you can prove is that you take some small open set. I already talked about this one in some sense. So that's why in the Carleman estimates, that's where you're going to observe things. And for control problem, that means where you're going to control. For inverse problem, that's where you will measure things. What you can prove is that if you take a linear combination of those eigenfunctions, but you restrict yourself to finite linear combinations with energy less than mu, I mean the frequency less than mu, and you take the L2 norm on the whole space, so that would be just the sum of the alpha j square. In fact, you can bound this by the L2 norm of the same thing, but restricted on small omega. I guess don't have to put those squares. Okay, so and the price you pay is that the constant blows up as you increase the limiting frequency. Like this. And this is the key ingredient. This has other applications like understanding the Hausdorff measure of the nodal sets of sums of eigenfunctions. This goes back also to the work of Pfefferman and Donnelly. But this was used to then construct the control function for this parabolic equation. What I mean by that means you start from any initial value and you can choose a function that which will act only in small omega, so it will be a source term that will only act in small omega and that will drive the solution to 0 in some final time t. So that was our motivation. That's what we proved here. I should review a bit some works that were done on proving estimates for non-smooth coefficients, with coefficients with jump at interfaces. There was this paper by Dubova, Osses, and Trail in 2002 where they proved such estimates for parabolic operators, but they had to assume some monotonicity conditions in the sense that they had to observe the solution on the side where the coefficients was the lowest. And this was a technical thing, as in those papers we proved that indeed you could observe on both sides. You didn't need this monotony assumption, first in 1D, then in several dimensions. With Luc Robiano, we then extended that. First we did that for elliptic operators, and we extended that to parabolic operators, which allows for controllability, allows you to treat nonlinear equations. And also, there's been some extension with Nicolas Lerner to anisotropic diffusion coefficients. Okay, so here, in what we do, all the steps are uniform in the small parameter delta. So that means we construct a control that can be seen as very robust with respect to those viscous perturbation in the interface. Okay, so now I will ask for the screen to be lifted, because I want to show things on the screen, on the blackboard. Because is Adrian here? Sorry. Okay. So in his lectures last week, Adrian Nachman at some point offered the possibility of proving Carleman estimates, and somehow nobody wanted to see that. But I thought it would be nice to show how you actually prove them for very simple operators, so that then we can see what the difficulty is in this more complex case. So I'm just going to consider the Laplace operator and show you how this can be done, and then we'll see this subellipticity condition appear. So this is basic stuff. As I said, I will first multiply by H2, so I consider the semi-classical Laplace operator. And then I introduce this operator. That means I conjugate with the weight function. And okay, I'll use D here will be H d over I, which is the standard semi-classical notation. And if you use semi-classical Fourier transform, then the symbol of this large D is psi, which tells you that the symbol of P, small p, is simply psi square. Now, you realize that when you do such thing, when you conjugate D with those weight functions, what you obtain is D plus I phi prime. Hence, P phi is nothing but D plus I phi prime times itself. And you can then write it. You can separate the self and anti-adjoint parts, and you write it as Q2 plus I Q1. And what are the symbols of Q2 and Q1? Well, if you develop that, you will find that it's going to be psi square minus phi prime square, and Q1 will simply be 2 psi times phi prime. Okay, here it's constant coefficients, but it's just a variation of that if you take varying coefficients.
What is phi prime? If you have many variables, then what's phi prime? It looks like derivative, but it's not. Yeah?
It's the gradient. Yeah. It's the here phi is a function of all variables. Okay, of all variables, yes. So the condition, what is the subellipticity condition is that you ask that when Q2 is equal to Q1 equals 0, that means when your conjugated operator, P phi, when its symbol vanishes, you ask for Q2, Q1 to be positive. And this is why we get strong estimates. In inverse problems, sometimes people derive weaker estimates with limiting weights. I mean, going back to the work of Koenig, Schuster, Ullmann, and the work of Dos Santos, Koenig, Salo, and Ullmann. And then they ask for 0 here, which then you need convexification, further convexification of your weight function to obtain proper estimates. But here, I'll stick to standard things. How do you obtain that? Of course, you could wonder. Well, it's quite easy. You take psi that depends on x such that psi prime doesn't vanish in your open set and all the way to the boundary. And then you can convexify this. And you can take, for instance, a very standard way and would be to take the exponential like this and take lambda large. Well, if you do that, you can prove that this is true. So this is quite easy. You know, if you go to more comprehensive studies of Carleman estimates, people will look at order M operators, and here there's an advantage. This is second order with real coefficients. And usually you find strong pseudo-convexity condition, pseudo-convexity condition. In the case of second order elliptic operators, those are trivial conditions, and this is all you need. Okay, so let's see how we can use that. You see, the idea is that when those two terms are going to be weak, this will have some strength. And this is the symbol of a commutator. So let's see how this commutator shows up. So let's consider P phi. Well, first you look at Pu equal F, and then you introduce V, which is exponential phi over h u, and you discover that P phi V is exponential phi over h f, which I'm going to call J now. What you do next is that you take the L2 norm of J, which is going to be Q2V plus Q1V square, plus, at first, you would write this. But since Q1 and Q2 are both self-adjoint, this is, of course, nothing but this commutator. And there we are. The symbol of I Q2 Q1 is H, because we're working with semi-classical operators, so we gain an H, and it's H Q2 Q1. Okay. And now, well, one way to view things is to take mu such that mu h is less than 1. Mu is meant to be large, but h is meant to be small, so you can do that. And then you find JL2 would be larger than some h, and then I have mu Q2 square plus Q1 square plus, so I over h Q2 Q1 commutator this will act on V times V. Okay. And what is the symbol of this? Well, the symbol of this is mu q2 square plus q1 square, the semi-classical symbol, plus q2 q1. And there you see the need of the subellipticity condition. You want positivity, so that behind this is Gaussian inequality. And so you need to show some positivity here, but when q2 is small and q1 is small, then you don't get positivity from this, and you get this from here. So what you can prove is that if for mu large, you can get this, for instance, greater than xi squared. And so with Gaussian inequality, Gaussian gives you that GL2, which is nothing but P5V. Here there's a square missing. Sorry about that. I should put it back here. Is greater than constant H, and then you get, for instance, the semi-classical H1 norm. And there you're done. You go back to U and you get your estimate. So you see Carleman estimates are easy to prove, those types at least. Everything is here, it's just a subellipticity estimate.
Ron, can you please repeat how mu disappeared?
Mu did not disappear, mu is here.
So how it appeared? Why G
Oh, I said mu so that mu H is less than 1. So why do I do that? Because this is, you see, this is, what is the order of that? This is second and this is first. So that will be second order. But Q2 is fourth order. And so, there's an H here. So I cannot, semi-classically, I cannot compare those. So I do this trick so that then I factor an H out. And now, semi-classically, I can look at the symbol of this whole thing and apply Gaussian inequality. Okay. So that's a very elementary proof. And now we've seen that basically what's there is just an integration by parts. I mean, there's, 99% of analysis is based on integration by parts.
It's all the same.
Or, okay, Cauchy-Schwarz also plays a role every now and then. So I'm going to go back to my slides. If you could get the screen down. If we could get the screen down. Well, if not, I can start explaining where the problem is going to be. If we apply this program to what this interface problem, what will happen? Well, you perform those integration by parts, and you will have terms, of course, that will live at the boundary. And well, then you need at some point to get some positivity of those terms. You need to, you see, at the end I managed to get positivity for trace terms. So there comes the questions. I mean, how do you treat those terms? Well, if you apply this program, you will end up with some stuff at the interface that you won't be able to control. And that was, I showed you this earlier paper by Dubova, Osses, and Frel. That's what they did. And that's why they had to additionally introduce some monotonicity conditions on the diffusion coefficients. So the idea now is to look at our conjugated operator and its properties at the interface. So basically, if we want to bring the analysis to the interface, well, there's one way to do that. It's Calderon projectors. And that's what we're going to do. But for this, you need to understand how elliptic, well, the elliptic nature of the elliptic nature of the operator. The original operator is of course elliptic. The conjugated operator is obviously not elliptic, so you cannot always do that. Okay, so I'll go as quick as possible, but I want to give you some ideas of what goes on here. So even though we have to work in the whole neighborhood of S, let's forget about that and let's work locally. So S is xn equals 0, then we have some x prime additional conditions. Xn large will be the right side, xn positive, xn negative will be the left side. So we might use some R and L to mean left and right. And what we have on both sides, this is the symbol, and what you have at the interface, let's say this is the symbol. For simplicity, of course it's a bit more complicated. So we conjugate the operator, and we get very similar things very similar to what I wrote on the board, but we have the thing on the right, on the left, and at the interface. And the problem now, after conjugation, look like this. You see dxn was changed into those things. And for simplicity, you may even want to think that phi only depends on xn. And this I already explained. Those are the symbols. What is important is that on both sides, okay, you see it looks pretty much like what I described, and what you can always write is you can factor things, and you would have two roots. You see? Just for the Laplace operator, you can do that, because for the Laplace operator, you get psi n, you get psi n plus I, psi like this, times psi n minus I. So you see, interestingly enough, they are both purely imaginary, and they are separated by the real axis. And that's what we're kind of after. Okay, so the ellipticity properties of those operators depends on the positions in the complex plane of those roots. And also, what is important for what goes on at the interface, and that's our additional difficulty here, is where does the characteristic set is? Where does it sit? So once we look at what goes on at the interface, we know we have the continuity of the solution, and we have this additional transmission conditions. So in some sense, this is the same thing. So we have three unknowns: the value, the trace, and the trace of the normal derivative on both sides. So that's three unknowns. And in some sense, this we already used, so we have only one equation. So to solve what goes on at the interface, we need two additional equations. I mean, that's what people in algebra would tell us. So we need, and you see, if it solves an elliptic operator, if it solves an elliptic problem, then we can have an additional relation. That's what Calderon projector tell you. But if it doesn't really solve an elliptic equation, then this is not going to happen. Okay, here is what comes out of this analysis. If the two roots that I just described are in the lower complex plane, then this is excellent, because all the analysis goes with contour integrations in the upper half plane, and there's no pole there, so everything that would be a problem vanishes. And in fact, what you obtain is that you obtain estimates of the two traces with respect to the right-hand side of your elliptic equation right away. It's like given to you. So you get two relations for free. So this is what I would call a very good configuration. When they are separated like this, well, we are back to the Laplace case. So this is not so bad. At least we get one relation. I mean, with the Laplace equation, you can relate the Dirichlet data and the Neumann data. This is pretty much what goes on. And this is a catastrophe. Here, there's nothing you can do. There is no relation between the traces. And then there are some intermediate cases, but I think I should not talk about that here. So you can quantify this. This is our symbols, the same as what we had before. You can form this quantity, and well, why this quantity? I mean, this you need to look at some details. But when this is positive, this is very good. When this is okay, when this is anyway, depending on this, for the low frequencies, that would be this negative. That this is very good, but it turns out to be very bad on the left-hand side. So you see, we have those we've chosen in fact, we choose our weight function such that we can find this. Maybe it's easier if I explain with this cartoon. This is the tangent frequency that, and as it increases, for what's on the right-hand side, you are in a fairly good situation for high frequencies, and you're in a fairly good situation for also what's on the left-hand side. So then you find two relations, additional relation, and you're done, because you can estimate what's at the interface. Yes. And it turns out for low frequency, you're very good on the right-hand side. So in some sense, you get two additional relations for free, and through transmission conditions, you can obtain what goes on the other side. And you don't care really what goes on the other side. And that's why you don't care if it's no relation coming from the left-hand side. Okay, so the whole scheme of the proof is to microlocally decompose phase space like this. The tangent phase space, because psi n is a preferred direction. And you obtain estimates in all those microlocal regions, and at the end you have to patch them together. So that's the idea. And where does this bad term comes from? Well, it comes from the fact that at the in this region here, we have the characteristic set of this operator. And the situation is really bad on the left-hand side. There's nothing you can do. But it's really good on the right-hand side. On the right-hand side, you get estimates of the two traces. And you want to transfer that to the left-hand side through the only thing you have left is this transmission condition. So you want to, you see, you want to invert. Let me think. No, sorry. You so you have things on VR, and you want to see things on dx and VL, and you have this 1/delta here, and this is what is going to make your life not easy, and that's why this 1/delta will show up in your estimate at the end. So this is unfortunate, but this is really there's nothing you can do about it. Well, at least when you use this technique. So I'm pretty much done, so I won't talk about the things. Those things can be extended, as I said before, to other geometries, like on manifolds and so on. You can consider several interfaces, but they should not cross. And so I have plenty of open questions. Do we have optimality of those powers? I mean, like we have, as I told you, we have this bad term, which has this delta term. But is that optimal? I have no idea. Can you produce also parabolic estimates? That would be for the controllability of nonlinear parabolic equations. I think the answer is yes, but that would be fairly technical. Yeah, could we consider non-conformal metrics? What happens if the interface touches the boundary? And those are also strong Carleman estimates. What can you do with weaker ones, like limiting Carleman weights that could be useful for applications to inverse problems? And I think that would be a difficult question, but a very interesting one. So I thank you for your attention.
Oh, thank you for the very nice talk. Are there questions?
It's Thursday morning.
Yeah. Can you say a few quick words about the construction of the weight function?
Well, here, yeah, as I described, I mean, this is rather, sorry about that. It's just, here the weight function is easy to build because you don't ask much. You just ask for you take something with a non-vanishing gradient, and you ask for you ask for this on the right to be larger. You know, the slope on the right to be larger than. So basically, your weight function, if you just look at the xn dependency, it would look like something like this. And you want to observe on this side.
Right.
Then you take it to be fairly flat in the other direction, and then once you've done that, you can take these things and take lambda sufficiently large, and you have all the thing you need for these type of estimates. This can be quantified. In fact, you can have let's just think of the standard transmission problem. Then you can actually give very precise relations between those two things, and if they are satisfied, then you have your estimates. If they're not satisfied, then the estimate is not true. In the sense that you can construct at the interface a quasi-mod, and that will actually make your estimate blow up if you send the large parameter to infinity. So you can find sharp conditions, and this is related to the psi condition of solvability of pseudo-differential equation. Of course, because what's behind this, like what people do when they use those estimates to solve equations to find complex geometrical optic solutions, and so it's related to solvability. And if you don't have these those jump conditions, then in some sense you won't satisfy the psi. Actually, it would be psi bar. So not solvability, but a condition. Yeah.
Okay, so thanks very much. We'll continue right away. Let's take